rearrange the formula for the area of a circle for R. So just have a go at that now. Think about what is the formula for the area of a circle, and then rearrange it so it reads R equals something. Formula then for the area of a circle? Okay. Whoops. We're after getting R on its own. First thing to do. To get R on its own, what would you do to the right-hand side? Right. Take away pi. You want to get rid of it, but how do we get rid of it? You don't mean take away, do you? Yeah. And take it away, I think that's what you want to do, but how do you do it? Divide by pi. Divide both sides by pi. Because if I divide this side by pi, pi's cancel. I'm left just with the r squared. That's what we're doing. But if I divide this side by pi to get rid of it, what must I do to the other side? The same. And that's the key thing to remember. I can do anything to a formula so long as I do the same thing to both sides. It can't be wrong. It's not necessarily useful, but it won't be wrong. Okay? If I divide both sides by pi, I get a over pi equals r squared. And then square root. How do I get rid of square? Square root. So r, putting the subjective formula, which is traditional on the left-hand side, is a square root of a over pi. Okay. So if I had a circle and the area was 364 square millimeters, calculate on the calculator for me what the radius of that circle is to an appropriate accuracy. And what I also want to do is to do it in one hit on the calculator. So you're going to hit the square root button on the calculator and then the fraction button, and you get the fraction symbol inside the calculator, however it looks like on your calculator, with a flashing cursor, and then you put the area on the top, which is 364, and then on the bottom you put pi, and then you hit equals. So it does it in one hit, and you get 10.764. Presumably a few more decimal places, but you're now going to round it to how many significant figures? Well, 3 is appropriate, Tyler. You've got 3 there, haven't you? Okay, 3 or 4. So what would it be to 3? 10.8 unit. It's a radius, so they're measured in millimeters. No. And what goes at the end? Right, okay. Let's get into the habit of doing this, okay? So, as part of another major calculation, you needed to know what the radius of that thing was. If there was some component with it and you knew this cross-sectional area, or you knew what the cross-sectional area had to be, 364 square millimeters, it's not inconceivable that you'd have to do a little calculation like this. So you'd remember the formula for the area of a circle, you'd do a quick back of the envelope calculation to get the formula in the correct form, and then you do it on your calculator and done. Okay, showing competences with mathematics as an engineer. There's another formula. Rearrange that for A. I'll just give you a couple of minutes, then we'll look at it together. Okay, so I want to get A on its own. What's the first thing to get rid of, Zach? B squared. How would you do that? Excellent. So what do I write on the left? Equals, yeah. And then finally, square root. So A equals, putting the subject on the left. Okay. Done. Hopefully you all got that. Anybody recognise this formula? No, not the quadratic thing. It's Pythagoras. So here we are again, a little engineering scenario. I want to know what this side is, and I know that this is, and this is, and so that's again a little component, and I need to know what A is. So I'm going to remember the formula for Pythagoras, little back of the envelope calculation to get it in the right form, and then I put the numbers in. So what is A to an appropriate accuracy? Again, do it in one hit on the calculator. So give me the answer with a few decimal points. 10.7. That was almost the same as the last question, wasn't it? That was weird. Anyway, so first question, does that look right? Why? Because it's less than hypotenuse, excellent, which it must be. So first thing, so you put that in, and now then, what's an appropriate accuracy? 10.78, okay. Unit, millimeters to 4 significant figures, yeah. Could have gone to 3 because this bottom one here is only 3, but we've got the option of going to the least accurate or one more. So 4 is appropriate, but so also is 3 significant figures. Rearrange that formula for V. Okay, let's have a look at it. Now, half, it's a bit weird this half thing. We've talked about years, I think last year we talked about this being the same. A over 2 is the same as a half of A. A half of something is the same as it divided by it. So, probably think of this as, if you're struggling, think of it like that. Now, how do I get rid of the 2? Times both sides by 2, okay? Not immediately obvious if you see it written as a half CV squared. What you need to realise is that 2 is underneath. So I'm going to get 2W equals CV squared. So that's the awkward step, in a way. And then it's the same as we did really for the area of a circle, isn't it? What do we do next? Divide by C. So 2W over C equals V squared. And then again, square root. So V equals the square root of 2W over C. What voltage will be required to give that energy stored on the capacitor? 2.43 joules if the capacitor has that value. So again, got to think about engineering notation, and we want to put it in one hit on the calculator. So again, hit the square root button, then hit the fraction button, and then you can put the numbers in directly into the calculator. 2 times 2.43. Yeah, how many micro is 10 to the minus, no, that's milli, minus 6. So it'll be 136 times 10 to the minus 6. So that's what you're going to key into the calculator. $189. A unit? Volts, yeah, we're after voltage, so volts, yeah. Is that an appropriate accuracy? No. 3 significant figures, so what would it be to 3? 189 volts. Okay. There's another formula. X subscript C, which stands for the reactance of the capacitor, equals 1 over 2 pi FC. So rearrange that for C. And then I'll give you some figures and we'll work out a value. let's have a look at this then. This is, there's one or two ways you can go about this one. So let's just have a look at it, and then you can write down one of the ways or both if you want. So let me run through them. Okay. Again, like one we just looked at, it's sort of worth thinking about what this actually means and how we can play around with it. It's 1 over, it's the inverse of 2 pi fc. So one way to go about this is to invert both sides, and then you get the 2 pi fc at the top. But to invert it, I need to realise that this means xc over 1. Whenever you've got a number, again, this is sort of basic fraction idea. Here's a number 3. We're used to seeing that as a number 3, but what does it mean? It actually means 3 whole ones. That's obvious. So we could write it as 3 whole ones, 3 over 1. So what's the inverse of 3? A third. In the same way, what's the inverse of xc? 1 over xc. So if I invert this side, I get 1 over x subscript c, which means the reactance for a capacitor, equals, now I can invert the right-hand side, which is just 2 pi fc. So now the thing I'm after, which is the c, is at the top. I have inverted both sides to do that. Now I ask myself the question, how do I get c on its own? I divide both sides by 2 pi f. So I've got c, or 1 over xc 2 pi f equals c. And I've rearranged that formula for c. The other way to think about this, and you might find this easier to think about, is take this original formula, and if the thing I want to isolate, which in this case is the c here, if the thing I want to isolate is at the bottom, and I think we talked about this sort of thing before, the first step is multiply both sides by c, and then it will be at the top on the other side. So the other way to do it is actually multiply both sides by c, and you get xc multiplied by c equals 1 over 2 pi f. So I've got the c, which is what I'm trying to isolate, and on it at the top now. Now the next step is to divide both sides by xc. So c equals 1 over 2 pi f xc, because now it goes underneath with the rest. So same answer, slightly different way to think about doing it. Okay? So sometimes the thing you're trying to isolate is underneath. And so there's two ways to do it. This first way, by the way, when you isolate it by inverting both sides, only works if there's only one fraction on both sides. Remember what we talked about before. So if you've got two fractions, this method on the left here won't work. You have to use this idea. Okay. So now we've got this formula, we can find the capacitance. So given that the frequency is 50 Hertz, which is common for this sort of thing, that xc is 3.6 milli ohms, because that's measured in resistance, if I remember rightly. Then calculate for me what c is, please. So using this formula, again, I'd use the fraction button, probably, and then I could type in 1 over, so I put 1 at the top, and then underneath 2 times pi times 50 times 3.6 times 10 to the minus 3. 0.88, what do we measure capacitance in? Farads. And that would be to two significant figures, presumably. So never forget to put the unit in, and if you've rounded it, the accuracy.